Hi everyone, welcome to video 2 of multiple linear regression. And so let's just take a few moments to review what we went over in the last video. Come on. So first, when do we use multiple linear regression over correlation? Right? So in correlation, right, we have one IV, one DV, and both are continuous, right? Both are continuous variables. So you have one continuous IV, one continuous DV. We have two continuous variables, and we want to examine the relationship between those two continuous variables. We use multiple linear regression when we add a second independent variable, right? A second continuous independent variable. So in the first lecture example, we examined the relationship between math anxiety and confidence. And now, for the first lecture example for multiple linear regression, we're adding stats anxiety as a predictor, right? So we use multiple linear regression when we have two or more continuous IVs and one continuous DV. So multiple regression is most useful when the independent variables are strongly correlated. If you remember in the last video, we saw what happens as the independent variables become more correlated with each other, right? So as the correlation between the independent variables increases, what happens to the overlap between all three variables? What happens to this black portion where all three variables overlap? As the correlation between the independent variables increases, the overlap gets bigger, right? So the overlap between all three variables, this black shaded portion, gets bigger. So as the correlation between the independent variables increases, it's less clear if both independent variables will win or whether one independent variable will better predict the DV. So it's almost like we're having a statistical cage match, right? Where stats anxiety and math anxiety are both entering the ring at the same time to see which one wins out, or if there's going to be a draw here. Maybe both of them will uniquely predict the DV, right? Because that's what multiple regression is doing. It's assessing the unique contribution of math anxiety in predicting confidence and the unique contribution of stats anxiety in predicting confidence. It's providing us what's in this green shaded portion, what's in this blue shaded portion. So, as we said in the last video, let's get ready to rumble. So let's take a look at the bivariate correlations between all our variables to see what's going on, at least at the bivariate level here. All right, so let's see how math anxiety and stats anxiety correlate to confidence. And then let's see how much the independent variables correlate with each other. Right. So here is the correlation table from SPSS. And again, let's cover up the shit that we don't need to look at. So we'll cover up everything below the diagonal of ones here. And that leaves us with less to look at, a little bit more digestible. Right, so let's first look at the correlations between the IVs and the DV. Right, so what's the correlation between stats anxiety and confidence? That would be negative 0.43. And we do have a significant negative correlation between stats anxiety and confidence. And then we also see that there's a significant correlation between math anxiety and confidence. And this should come as no surprise because we already looked at that relationship, remember, when we first talked about bivariate correlation. That was our first lecture example. But now we can see that stats anxiety is also strongly negatively correlated with stats confidence, right? So both independent variables strongly correlate with our DV, And we also see that math anxiety and stats anxiety are strongly correlated with each other. There's a strong negative correlation between math anxiety and stats anxiety. So here, all variables are strongly correlated with each other. So we have a perfect situation in which to do a multiple linear regression analysis. We want to know the unique contribution in stats anxiety and how stats anxiety and math anxiety predict confidence. What's the unique contribution of stats anxiety? What's the unique contribution of math anxiety in predicting confidence here? So does math anxiety better predict confidence or vice versa? Because you may, at first, you might be like, oh, math anxiety has a slightly numerically higher correlation, just in terms of absolute value here, just looking at the magnitude. You may think, well, math anxiety has a slightly higher numerical correlation value, 0.45 versus 0.43. That's negligible here. It is possible math anxiety may win out. It is possible that stats anxiety may win out, or maybe a draw. Maybe both of them will uniquely, significantly predict our outcome. We'll have to see. So what will the Venn diagram eventually look like, right? So in this case here, right, we have an equal stats anxiety and math anxiety. Both have, the blue shaded portion here and the green shaded portion here are equal, similar in size, right? So in this situation, stats anxiety and math anxiety both equally predict confidence. Right. But it is possible that the blue shaded portion is significantly bigger or the green shaded portion may be significantly bigger. We just don't know yet. It's possible, that the blue shaded portion may be bigger, maybe possible that the green shaded portion may be bigger, or they're about equal. We will see, right? So what we need to check before we take a look at the multiple regression output here, the simultaneous multiple regression output. We need all our variables to approximate normality, just like for bivariate correlation. And then when you do a multiple regression analysis, you can actually get Cook's d-values to check for potential outliers, which is nice. So we've already talked about Cook's d-values, so I won't go over that again. And then lastly, the last data check that we need to do for multiple regression is called homoscedasticity. I messed that up. I got in my mind and I was like, I'm going to pronounce that incorrectly, and I did. So homoscedasticity. It's sort of like the equality of variance assumption for regression, right? So we're going to briefly talk about homoscedasticity, briefly here, right? So we're always going to be a little off in predicting the outcome, right? We're trying to find independent variables that explain the variability or differences in whatever outcome that we're looking at here. We're in this case, we're using math anxiety and stats anxiety to predict how confident people are in doing well in the course, right? But we're not going to find perfect relationships here, right? We don't see correlation values equal to 1 or near equal to 1 here, where there would be a perfect relationship, meaning that if we know your score on the IV, we can perfectly predict your score on the DV. So we're always going to be a little off in predicting the outcome. Sometimes way off, sometimes, but we'll at least be a little off here, right? So there always will be some level of error, right? That we're going to use the IVs to try to predict the DV, and it's not going to be perfect. So there's going to be a little room for error here. So when you do a multiple regression, every single participant will have their own level of error. In multiple regression, we sort of call this the residual, right? And so this is just the difference between the predicted value and the actual score, right? So knowing your score on the IV, the analysis would predict, your score on the DV to be this, right? But it's not going to be perfect prediction. It's going to be a little off. So this residual is just the difference between the predicted score and the actual score. And so you get this residual for every single participant, and then you can plot those residuals in a histogram, right? So if you actually did this analysis, you get a new variable in SPSS, this residual variable, and then you would just run frequencies and create a histogram on these errors. And the errors for every participant should be normally distributed. And so this is the histogram for this residual variable. And as you can see, this is the distribution here, it looks fantastic. That it's approximates a normal distribution, right? So you just want to make sure that these residual values approximate a normal distribution, and so that's homoscedasticity, right? So yeah, that's homoscedasticity. And we've met in this case, and that's great. So that means that we can move on to the main analysis, but we'll save that for the next video.